Today we start our last chapter of the semester. Yep, we are getting close to the end. And today we're going to start talking about free radical chemistry. And so, in doing so, I'll give you a little bit of introduction as to why this is important for everybody. I'll talk a little bit about the homolytic bond dissociation enthalpy. And hopefully we'll have some time to get to free radical halogenation, another way of introducing a halogen atom into an organic molecule. But as I recall, many of you have desires to go on to medical school. And it turns out that free radical chemistry is extremely important in biology. Free radical chemistry is responsible for aging. Free radical chemistry is responsible for pain. Free radical chemistry is responsible for fevers. Free radical chemistry is responsible for cancer. There are a lot of things that free radical chemistry is actually involved in a biological system because biology is mostly in water. And all of the mechanisms that we've learned so far in terms of nucleophiles, they've been fairly strong bases. And those bases can't exist in water. They would become protonated. And so we have to have another way to do the chemistry that we're talking about. And it turns out that it's free radical chemistry. A free radical is what? Pardon? Yes, that's right. So any molecule that has one or more unpaired electrons is a free radical. Okay? Now, one of the common free radicals that you all are inhaling right now is dioxygen. Dioxygen is in what we call the triplet state. If you recall back from your general chemistry, it's got two lone electrons, one on each oxygen atom, and they are not spin paired. Okay? It is a free radical that we're breathing right now. It is responsible for us living. It is also responsible for us dying. Okay? That gives life also takes it away. Okay, so we're going to talk a little bit about some of these free radical reactions today. This is an example from a book called Molecules in Medicine. It was published about 10 years ago now by a very famous chemist, E.J. Corey. He won a Nobel Prize in the early 90s for his entire body of work. He is probably the most prolific scientist in all of history. He has more citations of his work than any other scientist in all of history. He's still at Harvard, and I believe he's about 92 or 93 now. He's still working, okay? Doesn't do a whole lot in the lab anymore. I think he still has an active lab, but he's publishing more of these general books these days. This is a great book if you're thinking about going into medicine to buy. It's not hard to read. It's written for the layperson, but it talks about molecules and how they've been used as medicines, and it talks about some of the general chemistry behind the molecules. So it's a great book. And one of the examples that he uses is arachidonic acid. Here is arachidonic acid. What can you tell me about arachidonic acid? It's got alkenes. Very good. What else? What other functional group does it have? It's got a carboxylic acid, hence arachidonic acid, right? So we call this, it belongs to the family of fatty acids, okay? Arachidonic acid has what's called a cascade reaction. And when you get to medical school, you'll learn about the arachidonic acid cascade, especially if you end up doing research in medical school. And the arachidonic acid cascade, if you've ever seen it, all the known reactions of arachidonic acid would more than cover twice the number of boards that we have in here. And you'll have to learn stuff like that, okay? So it's a lot. So, but anyway, let's talk a little bit about what arachidonic acid can do. So here's an example. So arachidonic acid has these hydrogens that sit on these carbons between two alkenes. Can anybody tell me what these positions are called? When you have a position that is adjacent to an alkene, what do we call that? Vinyl is on the alkene. So we had vinyl, we had allyl, allylic position, right? So this is the allylic position, and it's actually allyl to two alkenes, and so it's actually very reactive. And the hydrogen atom can be readily abstracted from another species. This is a tyrosine radical. that exists in the enzyme cyclooxygenase 1. Okay? Now, cyclooxygenase 1 has this tyrosine that can form a free radical, and it can abstract a hydrogen atom. Notice what kind of arrows are we using here? Single barb or fishhook arrows, right? And so we're moving an electron at a time. So what is this saying? It's saying that this lone electron, this lone unpaired electron on oxygen is reacting with this hydrogen. This carbon-hydrogen bond, one of those electrons is going to the oxygen to form a new oxygen-hydrogen bond, and the other electron's going on to carbon-13. Not C13 as in the isotope, but just number 13. Okay? And so you end up with this, what we call carbon-centered radical. It is resonance stabilized. Okay, so it's fairly easy to make. And now it can react with oxygen because oxygen is also a radical species. And these things will react and form these so-called endoperoxide units, PGG2, which when you get to medical school, you'll learn what all this PGG junk means. Okay? This then gets reduced to an alcohol, and then this rearranges to what's called PGE2, which is a prostaglandin. There are numerous prostaglandins in biology, okay? But prostaglandins are a very, very important biomarker that physicians look for. So, for example, when my wife was working at Vanderbilt Medical, they did analysis on PGE2 and other prostaglandins all the time to try to determine what the disease states of certain tissues were. Okay, so she spent a lot of time analyzing these molecules, and she actually analyzed these molecules using mass spectrometry, which we talked about last chapter at the very end, because these things are only produced in very small quantities in biological systems. So you have to have a very sensitive technique to detect them, and so that's what they would use. Turns out, again, if you get inflammation, it's a prostaglandin that's causing that. People with arthritis, it's the prostaglandins that are causing that. If you get a headache at the end of this lecture, it's because a prostaglandin is giving you a headache. Prostaglandins are very, very important in a number of disease states or ailments, okay? And so it would be great if we had a medicine, right, that could help block this kind of thing. So what do you typically take if you get a headache? Typically take something like Tylenol. What would be another one? Ibuprofen. And it turns out that ibuprofen is really good at inhibiting the cyclooxygenase 1 enzyme, okay, or as we call it, COX-1. There are several COX enzymes. But if you look at the active site of the COX-1 enzyme, which we've got a crystal structure of these days, what you can see is there's the tyrosine 385. It's a radical. And notice that the arachidonic acid can fit in what we call the active site. Okay? So arachidonic acid gets into the active site, the tyrosine radical abstracts the hydrogen, and then all the chemistry happens, okay, that we just talked about. Well, what happens when you are having a headache or whatever, or a fever, this is what's happening, and this triggers the response that you all get. When you take ibuprofen, the symptom goes away, right? And the reason is because ibuprofen will sit in the active site near that tyrosine 385. Okay? And because it's sitting there, what does that mean can't be there? Arachidonic acid. Okay? So this inhibits the cyclooxygenase 1 from doing its chemistry, which means that the prostaglandin synthesis is increased or decreased? Decreased. And if it's the prostaglandin synthesis that's responsible for your aches, pains, fever, and other things, then what happens to your symptoms? They go away, right? And so that's how ibuprofen works. It blocks the active site of cyclooxygenase 1, keeps the arachidonic acid from getting in there and doing the chemistry that it's known to do. So this is why it's important for you all to know something about free radical chemistry, because when you get to medical school or you get into your higher level biology classes, you're not going to be pushing double-headed arrows very much unless you're making stuff in a flask. Because in biology, things are done in water, and it turns out that free radical chemistry can be conducted in water because a free radical is not a base. Okay? That oxygen atom is not negatively charged on that tyrosine, is it? It is neutral. Okay? So it doesn't function as a base, but it can do other types of chemistry. Okay? And so that's why Mother Nature uses this free radical chemistry, because we are water-based. Well, actually, we're dirty bags of water, if you really think about it, right? That's what living things are. So far, every reaction mechanism that we have dealt with is a heterolytic mechanism, meaning that we're pushing 2 electrons at a time, right? So if we look at this example where we have a terminal alkyne, right? So we don't care about what's attached there. It's just a methyl group right now, but that's not important. We've got the carbon-carbon triple bond. We've got an acidic hydrogen. Can anybody tell me about where the pKa for a terminal alkyne is? Ballpark it for me. You want to take a guess, Anna?
Guess 25.
You're exactly right. Around 25, right? It is around 25. Anybody want to take a guess where the pKa for ammonia roughly is? Higher or lower than 25? Higher. It is higher because we need a stronger base to react with the acid for it to go to completion, right? And so we would push the arrows as such. We are using a double-headed arrow. We get the alkylide, right? The equilibrium lies to the right because we have a really strong base and a really good acid, relatively speaking. This then can react with something like methyl bromide to make a new carbon-carbon bond. We've talked about all these types of reactions before, right? Nothing new there. But again, we're pushing 2 electrons at a time. What would happen if we tried to do this chemistry in water? So Jack comes in, he throws all this stuff in water. What happens? What's the pKa of water? Come on, I know we've had a weekend. What's roughly the pKa of water? 16-ish. Yes. So stronger acid or weaker acid than the alkyne? Much stronger by several orders of magnitude. So when Jack tries to put his sodium amide base in water with the alkyne, what happens? It only reacts with the water. That is the leveling effect that you learned about in 107. You can never have a base stronger than the conjugate base of your solvent, right? So if we've got water and we throw in a really strong base, the only thing that can actually exist in water as a base is hydroxide, right? Which is not strong enough to do this chemistry, and we say that the reaction has been quenched. In other words, the water reacted, it didn't do what we wanted it to do. It's a bunch of crap, we got to throw it down the drain and start over, right? That's why we do this type of chemistry in things that are organic. We don't do these types of reactions in water in the laboratory. All right? So instead of pushing 2 electrons at a time, we're going to be pushing a single electron at a time. We're going to be talking about bond homolysis. So if you take a molecule that has 2 atoms, here A and B, notice we're using a single barbed arrow. We are going from the sigma bond. 1 electron is going to A, 1 electron is going to B, and we generate a pair of radicals. Okay? It is extremely important that you pay attention to the type of arrow you use when you're doing stuff on your homework, on your exams, etc. Because a double-headed arrow, even if it's pointing to the right atom, is wrong. Okay? You've got to use the right arrow. Here are some common radicals that we will be discussing in this chapter. Chlorine atoms, as they exist on the periodic table, are radicals. They do not have an octet. They have 7 electrons around them, and one of those electrons is unpaired. Methyl radical. It's a methyl group with a lone electron. Does that satisfy the octet? No, it does not. It's got 7 electrons around it, right? We learned that we can't create methyl cation very easily anyway, right? But we can actually generate methyl radical. It's electron deficient, just like a methyl cation is, but it's not as electron deficient. It's not formally charged. And then hydroxyl radical, okay? Very reactive species that's responsible for a variety of things in the atmosphere, for example, and not so much in biology, though. We need to talk a little bit about BDE. Your book calls it bond dissociation energy. That's kind of correct. It's actually bond dissociation enthalpy. Enthalpy and energy are related, but not exactly the same. So I'm telling you what it correctly is, and then know that the book just talks about energy. And don't worry too much about the difference. So for example, if we took dihydrogen and we broke it apart into two hydrogen radicals, right? Does that take energy or does it release energy? It takes energy. All bond-breaking events are endothermic, and all bond-forming events are exothermic. So what we have here is hydrogen. Now it has its duet of electrons. It kind of looks like, each one kind of looks like helium. We can put enough energy into it, though, to generate two hydrogen radicals. That is endothermic, and so we would correctly draw this higher in energy than the starting materials, right? And so the energy required to break the bond homolytically is the homolytic bond dissociation enthalpy, okay, or the delta H of that particular reaction. And that's why you really need to be calling it enthalpy, because delta H is enthalpy, all right? So they're confusing the words a little bit here. It turns out to do that, you have to put in about 436 kilojoules of energy per mole. Is that a little or a lot? That's quite a bit. It requires quite a bit of energy to do that. This is a list of bond dissociation enthalpies in your book. You will need to memorize all of these for the exam? No, not really, right? I'm not going to expect you to memorize all this stuff, okay? But I am going to expect you to kind of know some rough things, okay? I always expect you to kind of know roughly where things are. Looking at that table, what can you roughly tell me? Okay. What else can you tell me? These things? Okay, yeah, these all have kind of relatively low bond dissociation enthalpies, don't they, compared to other things? So halogens, X2s, typically have lower bond dissociation enthalpies. That's good. What else can you tell me? Well, if you look at it, right, you can tell me that just normal alkanes have fairly high bond dissociation enthalpies, okay? Alkyl halides, the carbon-halogen bond is relatively low compared to some of the others. You can see that if you have hydrogens in the allylic position, for example, those are lower in energy than a typical CH. Let's see, what else can you, down here we have some things that have pretty low bond dissociation enthalpies. What are these functional groups where we have two oxygens bound together like this? Kind of looks like an anhydride in a way, but it's got an extra oxygen, right? So if we had like H2O2, what would we call that molecule? Hydrogen peroxide. The peroxides have lower bond dissociation enthalpies, okay? And it turns out that these oxygen-oxygen bonds in molecules like hydrogen peroxide or these diacyl peroxides, as we call them, they have fairly low bond dissociation enthalpies. And they're quite frequently used, for those of you in polymer chemistry or over in polymer science, these are frequently used as free radical initiators for the polymerization of monomers because they will split apart into radicals quite easily and go on and help promote the reactions. And so we'll talk about those reactions a little bit more. So if I need you to know these values exactly, I will give them to you. But what I want you to know is kind of where an alkane falls, kind of where a halogen falls, kind of where an alkyl halide falls. Peroxides, you need to have kind of a feel for that, okay? But if you need to know the exact value, I'll give you that value. Does that sound fair enough? All right, good. So let's look at a reaction. And this is kind of a fun reaction that you can actually find on YouTube. It's a pretty good demonstration. I've never really been brave enough to try it. But basically what you do is you take a tube, a glass tube, maybe about yay long, maybe about an inch in diameter, and you fill that glass tube with a mixture of hydrogen gas and chlorine gas. And you put 2 corks in the end of it, and you keep it in the dark. And what you do is you bring it up to the front of the room, you put it in a clamp, and nothing seems to be going on. And then you tell a student to come up and take a picture of it with a flash, and when the flash hits it, it explodes, and the 2 corks go out the end, and you form hydrochloric acid. Now, I can't do that in this room for a couple of reasons. Number one, it's confined, and I don't want broken glass going everywhere if that should happen, but also because of the hydrogen chloride that you generate, we'd start kind of choking on that in here, okay? So it's not, you need a bigger room with a little ventilation to do it. But it's kind of a cool reaction to watch. And so the hydrogen and the chlorine don't do anything until that flash goes off. What's that flash doing for us? It's providing the energy to get over that energy barrier. And once you get over that energy barrier, hydrogen and chlorine will react to form hydrochloric acid. Now, if you look at the bond dissociation enthalpies on those tables, you'll see that to break the hydrogen-hydrogen bond would be 436. To break the chlorine-chlorine bond would be 243. And the energy that you get out of forming the hydrogen-chlorine bonds would be 431. But you'd get twice that because you get 2 moles, right? And so you all will remember the standard enthalpy change equation from general chemistry. Delta H is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants, right? And you probably always wondered, well, why is it products minus reactants? Anybody ever wonder that? Anybody ever ask that question of Dr. Broom? Or did you just take him at his word that it's products minus reactants? Why is it products minus reactants? Can anybody tell me? Can anybody take a guess? Why would we set it up as products minus reactants, not reactants minus products? What kind of bonds are going on in the products? Bonds being formed or bonds being broken? Being formed, right? And those are going to be endothermic or exothermic? Exothermic. And the bonds that are in the reactants, are those being broken or formed? And those are going to be endothermic. And so when you do that, right, you're looking at products or bonds gained and the bonds lost, and you sum those up and you get the overall whether the reaction is exothermic or endothermic, right? And so it turns out that in this particular case, the reaction is exothermic by 185 kilojoules per mole. So that's favorable, right? So why didn't it just happen? When I was in the lab mixing the hydrogen and chlorine, why didn't it just happen? I've got a big energy of activation that I've got to overcome. I've got to break a bunch of bonds, right? And so even though it's an exothermic reaction, you still have to have energy to get over that energy barrier, and that's what the flash of your camera would provide. Although I don't know if the flashes on the new phone cameras would do it. The flash that they always used were the big flashes on, like when you had an SLR camera, you know, with film. Those put out a lot of UV light. I don't know if the phones now do that or not. But anyway, this reaction is overall exothermic. Now, you might be thinking that this reaction is hydrogen plus chlorine to give hydrochloric acid, as we just basically said, right? 185 kilojoules per mole. There should be a dot there for 2 chlorine radicals. This is not how the reaction occurs. The reaction does not occur where all the hydrogen atoms just break apart and all the chlorine atoms break apart and they all get together and recombine. That takes way too much energy. These are called chain reactions. Free radical reactions or chain reactions. We'll talk a little bit about those here in just a moment. But this isn't how the reaction actually occurs. It is a free radical process, but not all the hydrogen atoms just split apart and all the chlorine atoms just split apart and they find new partners. That is not how this happens at all, okay? And so we're going to talk about the mechanism for this particular reaction as well. You'll notice if you went back and looked in that table, not all the bond dissociation enthalpy values are the same for all CH bonds. What kind of hydrogens are highlighted in blue here? What kinds of hydrogen can we have? We have hydrogens on carbon, that's true. How many different kinds of carbon-hydrogen bonds can we have? This goes back to like chapter 2. Well, they are terminal, I'll give you that, but that's not what I'm after. Primary, secondary, and tertiary hydrogens, right? What kind of hydrogens are those? Those are primary hydrogens. And what you'll find is if we abstract a primary hydrogen to generate a primary radical, that takes about 423 kilojoules of energy per mole. If you look at secondary hydrogens, to get a secondary radical, what do you notice about the energy? Higher or lower? Lower. So does that mean it's easier to form or harder to form? It is easier to form. It is easier to abstract a secondary hydrogen than it is to abstract a primary hydrogen. Okay? And then, of course, we could also look at a tertiary hydrogen, the hydrogen on 2-methylpropane, to generate a tertiary radical. And what you'll notice is that takes 400 kilojoules per mole of energy to happen. What trend does this follow? How would you describe that trend? The more substituted, what? The easier it is to abstract a hydrogen atom. What other thing that we've talked an awful lot about does this tend to follow the same trend? So it says that primary is less than secondary is less than tertiary. What else does that follow? What else is tertiary greater than secondary greater than primary in terms of stability? Carbocations. The stability of free radicals and the stability of carbocations trend. But the cool thing is that whereas carbocations like to rearrange and causes all kinds of headache, radicals rarely do. Because radicals are not cationic. Okay? They are neutral species, and they are electron deficient, but they're not as electron deficient as a cation. Okay? You really have to know these bond dissociation enthalpies for a variety of molecules, and fortunately these things are in a table. So if you look at ethylbenzene, for example, you'll see that these are primary hydrogens, but notice that the amount of energy that it takes to remove one of these hydrogens is different than for just a normal alkane. The aromatic ring has an effect. Okay? You'll notice that getting the secondary radical here takes a lot less energy. Can anybody tell me why the secondary here has so much less energy than just a typical secondary? What is it about having a radical on this benzylic position that makes it so favorable?
The aromatic ring makes it more substituted.
Doesn't make it any more substituted, but it has something to do with the aromatic ring. What can that aromatic ring do? How? You're on the right track. How? What can I do with that radical? Notice I've drawn out the pi bonds. I'm giving you a hint here. Resonance. That's right. I can draw resonance structures. So I can draw resonance structures with free radicals just like I can with anions and cations. Okay? I just have to use some more arrows, that's all, right? And then I can draw other resonance structures for that I'm not going to show. But when we have a radical on either an allylic position or a benzylic position, those are going to be more stable. Those radicals will be more stable than a typical secondary radical, okay, because of the resonance contributions, and you can see that here. Okay. Now, this is from the slides provided by the publisher, and there's part of it that I hate, and I'm going to ask you why I hate it here in just a second. But one of the things that we learned, right, was that a carbocation gets stabilized by having more substituents because of this effect. This, what did we call that effect? Well, you can undergo a hydride shift, but that's not what we're showing here. We're just showing that the electrons here help stabilize that cation. It is hyperconjugation. That is right. This is the hyperconjugation effect. And the same thing can happen for a radical. That's why the stability trend for cations and radicals, they track each other. Okay? Now, the book does this crap. And why do I call it crap? Pardon? Okay, they do kind of look the same. They say that these are resonance structures. Is that a true statement? Why is it not a true statement? Pardon? Well, we can break bonds in resonance structures. We can form bonds and break bonds, as long as they're pi bonds. They broke a sigma bond. That's exactly right. And in doing so, what moved? The hydrogen moves. What can't happen in resonance structures? Atoms can't move. Right? Not saying that this couldn't happen, but that's actually a reaction, not a resonance structure. Okay? And so for some reason, the book tried to explain the hyperconjugation effect through this nonsense. Okay? I don't want to confuse you. Do not believe this nonsense. Okay? These are not, you cannot draw hyperconjugation in the same way that you draw resonance structures. And I think they tried to confuse it too much. So this stuff here, ignore this crap. All right? This is just through space, hyperconjugative overlap of orbitals. Okay? And so that's why you get the stability. Trying to think about it like this just hurts my head. Okay? And it should hurt yours. All right, let's talk about some real chemistry. One of the first things that you learn when you talk about free radical reactions is that halogen radicals will react with alkanes to make alkyl halides. So for example, if you take a chlorine radical, let's say it's just X is chlorine, it will react with something like methane or some other alkyl halide, and the halogen radical will abstract a hydrogen atom to generate a new carbon radical plus HX, so it forms HCl. That carbon radical then goes on and reacts more and forms the alkyl halide, and we'll talk about that mechanism in a moment. But we call this atom abstraction. X dot is abstracting a hydrogen atom. So it is a hydrogen atom abstraction to give a new carbon-centered radical. Okay? Would you expect that that reaction lies to the left or to the right? And how would you determine it? I'm breaking a sigma bond, but I'm also gaining a sigma bond, right? So it's kind of hard to tell there. What would you look at? You'd look at the bond dissociation enthalpies. You'd use the delta H equation, all right? And you would sum it up, and you would determine that the equilibrium actually lies to the right. The the carbon radical is actually a little more stable than the chlorine radical, for example. Okay, so this is some chemistry that we'll be learning about. Radicals also like to react with carbon-carbon double bonds, where the radical will attack the pi bond. Notice the arrows. You got to have 3 of them. The lone electron on the halogen here is reacting with one of the electrons from the pi bond and the other to form a CX bond, and the other electron is going to carbon to form a carbon radical. For those of you in polymer science, this is how radical reactions are started to form polymers. This is how you take styrene and a free radical initiator and you form styrofoam, for example. Okay? It's because these free radicals will readily react with pi bonds. Okay? Now, Ahmed had just mentioned, right, we are sacrificing a weak pi bond on the left, and we're gaining a strong sigma bond on the right. The equilibrium should lie to the right. And it does, right? We get a new radical, and that can go on and react further and give more chemistry and make a polymer, for example. Other things that radicals like to do is they like to react with each other. So if I had two, let's say, chlorine radicals, they will react to form X2, Cl2. Why is that? Why would two radicals want to react with each other?
Electron on pair.
Pardon?
Electron wants to be paired.
That's true. What else? What does every atom have over here that is not over here? Octet, right? Chlorine likes to have an octet, right? And so how can they get that octet? They could get that octet by reacting with one another and sharing those electrons. Radicals also like to react with oxygen because oxygen is in the triplet state. It is a diradical. Both oxygens have a lone electron. Okay? Now, we'll quite frequently just draw it like that and ignore the other lone pairs because they're paired up. So why does this not react to form what's called singlet oxygen? It is. That's true. Why is it?
The pi bond is more unstable than the sigma bond.
Well, I still have my sigma bond, though. I mean, can't I do this on paper? I mean, I broke no rules showing those two electrons coming together to form a pi bond, right? This is where our arrow-pushing formalism sometimes get in the way of what's really happening. Because I can do this on paper. You broke no rules. But this isn't how oxygen exists in nature. It exists like this. Tell me why. I'm not going to draw the entire orbital energy diagram for you. You can look that up. It's on Wikipedia. But when you look at the molecular orbital diagram for dioxygen, what you'll find is that there are two orbitals that are degenerate. They are at the same energy level. And they're the highest up, and they both have a single electron in it. Why is it that we would put an electron here and an electron here instead of both electrons paired in one orbital? Yeah, you all learned about the Aufbau principle and other things, right? When you talked about molecular orbitals in Gen Chem. It's coming back to haunt you a little bit, right? So you had these molecular orbitals that were degenerate. You start filling up electrons, and then you have two left, and you have to put them in each orbital, right? Until we have to go back then and start pairing up. So you can't just put them both in one. And so to go from here to here requires some special chemistry, and this triplet, or excuse me, singlet oxygen, as we call it here, is actually very reactive and quite toxic, actually. Okay. Radical scavengers. Radicals will also react with radical scavengers like vitamin E. Vitamin E, you learn is in your biology classes, is a good what? It's a good antioxidant, right? Facial creams and things like that, ladies, right? Filled with vitamin E. It's because we get wrinkles and we age because of oxygen. Oxygen does radical chemistry. Vitamin E fights that. It's an antioxidant, okay? And so, anybody know of any other antioxidants that we need in our diet? Vitamin E is one. It's also known as alpha tocopherol. Vitamin C is another good one. It's a water-soluble antioxidant. So you need water-soluble and you need fat-soluble antioxidants, and vitamin E is a fat-soluble antioxidant. And that's why they put it in facial creams, because skin is mostly lipids and oils and fats. Okay, and you need something that'll dissolve in that. Vitamin E will. Vitamin C does not. Okay? So let's look at the halogenation of alkanes. Here we have an example where you take methane gas from petroleum, you take chlorine gas that you generate from seawater, you mix these things together, you shine a bright light on it or heat it up really high, you can make methyl chloride plus HCl gas. Both of these compounds are commercially useful. HCl to make hydrochloric acid, CH3Cl to make an alkylating agent for like SN2 reactions. You can take cyclohexane, react it with bromine, again, shine a bright light on it, or heat it up really high and you can get bromocyclohexane or cyclohexyl bromide. How else could we have made cyclohexyl bromide, knowing the other chemistry that we've learned until this chapter? Pardon? Substitution of what? You could make it by substitution chemistry. How else could we have made it? How about the addition of HBr across a double bond? Right? But there we would have to have started with cyclohexene, reacted it with HBr, we could have gotten that. And it turns out that alkenes are not as common in petroleum as alkanes. And so you just don't have as much stuff to work with. So one way to make cyclohexyl bromide, and the commercial way to do it, is to make it from something like cyclohexane. Here we have these examples, the hydrogens are all the same. They're all either methyl hydrogens or secondary hydrogens, and so the product that you get is the same no matter which hydrogen reacts. However, in example 3, where we have propane, you'll notice that we have 6 primary hydrogens and 2 secondary hydrogens, and we actually get a mixture of both organic products. We get a mixture of 1 chloropropane and 2 chloropropane, or isopropyl chloride as it's called. And what's kind of weird about this is notice the ratio. Why is that weird? Why would getting a 1-to-1 ratio be weird here? Okay, that's true. You're getting there, but why is the ratio odd? You're getting more at the explanation of the ratio, which is correct. But why is a 1-to-1 ratio of products here odd? Why should you not have predicted that? How many primary hydrogens do we have here? We have 6, right? How many secondaries? 2. So that's a ratio of what? 3-to-1. That tells me that if I'm thinking about this just randomly, that chlorine radical should have 3 times the opportunity to react with a primary hydrogen than a secondary hydrogen. And if I was doing that kind of math, I would predict a 3-to-1 ratio. But I'm seeing a 1-to-1 ratio, so what is that telling me? This gets to your point. That's right. That secondary hydrogen is a lot more reactive than a primary hydrogen, and that's why you see an equal mixture here. When you shouldn't have seen. You should have seen 3 times as much of this stuff, right? Just based on statistics, and we don't. We see equal mixtures. Okay? Now, it turns out that we don't have you do these types of reactions in the lab because they're not very laboratory friendly. These are industrial scale reactions where you have big pieces of equipment and large acreage and all kinds of stuff. You don't have little flasks. And the reason is because this is a hard to control process. If you take methane and chlorine and you initiate it by shining a bright light on it, you'll get chloromethane. But that chloromethane is also reactive, and it will react to form dichloromethane, which is also reactive, which will go on to form chloroform, which is also reactive, which will go on to form carbon tetrachloride. You get a mixture of all these products. Not very useful on a laboratory scale. We like to do reactions where you get only one product. However, industrially, this is something I can sell, this is something I can sell, this is something I can sell, and this is something I used to be able to sell. Okay? This is a strong carcinogen. They don't sell it so much anymore. Okay? So you get a mixture. How do I get these things purified so that I can sell them to the people? Nobody wants to buy the mixture. Maybe Kaylin wants some dichloromethane to do some chemistry, and I got to send her just dichloromethane, right? So how do I separate these components of this product? What technique would I use that you all have talked about in lab? Distillation, exactly. This is a gas at room temperature, and the rest of them are liquids. So as the reaction occurs, this bubbles out, and then I take the liquid and I distill them, and I get the pure dichloromethane, I get the pure chloroform, and I get the pure carbon tetrachloride. And I put them in separate bottles, and I ship Kaylin the dichloromethane that she ordered, and I send Ahmed whatever he ordered, and we can do that, right? So it's really only useful for an industrial scale type of reaction. There are some facts that you need to know about these types of reactions. Let's look at the facts and what the explanation is here. Light, heat, or added peroxide is necessary for these reactions to occur. So you need light, which can initiate free radical reactions. You need heat, and by heat, I don't mean 20 degrees. Hundreds of degrees, usually. Okay? Lots of heat. Or peroxide. Peroxides have those weak bonds, and they can generate radicals pretty easily. Okay? So, oxygen will typically inhibit these reactions. These reactions, free radical reactions, typically don't work very well in an oxygen environment. That's because oxygen is a diradical, and it will react with any radicals that you make and stop the reaction. Free radical reactions, we typically don't see any rearrangement. So if you're wondering whether or not the chemistry that you're observing is free radical or going through cationic mechanisms, typically we look for rearrangements. And if we see no rearrangements, that's usually a good sign that the chemistry is going by a free radical mechanism. Okay? So I'm going to skip the energetics. I want to get to this before today is over. So all free radical reactions have 3 steps, or 3-step types. They can actually have thousands of steps, but they have 3 main types of steps. You need to know these by heart. They are initiation, they are propagation, and they are termination. And for those of you in polymer science, you will hear those 3 words over and over again until you're sick about it when you get into some of your higher level polymer science classes. Okay? Initiation, propagation, and termination. How would you identify an initiation step? Yep, it is the first one, but how would you identify it? Okay, we got the heat or the light, and what else? Notice on the left there are no radicals, right? Where are the radicals at? On the right. So when we go from no radicals to radicals, that's an initiation step. We can have propagation steps, but all propagation steps have something in common, and what is it? Radicals on both sides. We have a radical on the left, we have a radical on the right. And termination steps, how would you identify a termination step? No radicals on the right. So when 2 radicals combine to form something that is not a radical, that by definition is a termination step. So we're going to pick up with this again on Wednesday. Now, your stuff that you all worked on Friday, you're all getting credit for it for doing it, so don't worry about that. But I'm taking my time to make comments, so you'll get your comments back hopefully Wednesday. And I hope you found it kind of useful to kind of jog your memory. It was what? It was hard? It was supposed to be, right? It was supposed to be hard, okay?